I'd like to thank the organizers for inviting me and giving me an opportunity to speak in such a great conference. Today, I would like to talk about deformations of associative submanifolds in nearly parallel Z2 manifolds. First, we give an outline of today's talk. Well, nearly parallel Z2 manifold is defined by using the notion of Romanian cones. So first, we review the geometry of Romanian cones. And next, well, the typical example of nearly parallel Z2 manifolds is S7, seven-dimensional sphere. So we want to consider submanifold theory of nearly parallel Z2 manifolds. So for simplicity, we assume that the ambient space is S7 and define several classes of submanifolds in S7. And next, after defining some submanifolds, next we study infinitesimal deformations of these submanifolds, and finally, we study deformations of homogeneous associative submanifolds. Homogeneous. Well, in homogeneous case, we study the deformation space explicitly. So first we study the Romanian cone. About Romanian cone. What is Romanian cone? So first, let YG be a Romanian manifold, and then consider CY and G bar, which is R positive times Y and dr squared plus R squared and G. This is called Romanian cone. Well, roughly speaking, for Romanian manifold Y, consider the cone CY, cone CY. This is called Romanian cone. And then, by supposing that the Romanian cone has special holonomy, then we can define various classes of submanifolds. For example, if the cone is suppose that the Romanian cone is a Calabian manifold. Calabian manifold is a Romanian manifold whose holonomy group is contained in SUN. Then the corresponding manifold Y is called Sasaki-Einstein manifold. And as an example of Y, S2n-1 odd-dimensional sphere. Or the next example is a Stiefel manifold V2RK. These are examples of Sasaki-Einstein 2n-1 manifold. And next, we assume that the Romanian cone is a Z2 manifold. Here, Z2 manifold is a Romanian manifold whose holonomy group is contained in Z2. Then the corresponding manifold Y is called nearly Kähler 6 manifold. But we note that nearly Kähler manifold is not Kähler manifold in usual sense. Non-Kähler. The name is very confusing. So, and as examples of Y, we have S6, six-dimensional sphere, and CP3, and S3 times S3. And this, yes. And the next we suppose that the cone is a spin 7 manifold. Spin 7 manifold is a Riemannian manifold whose holonomy group is contained in spin 7. And the corresponding manifold Y is called a nearly parallel Z2 manifold. Well, and typical examples of nearly parallel Z2 manifolds is S7 And moreover, nearly parallel Z2 manifolds have many examples. So first of all, the Lie group spin 7 contains SU4, special unitary group. So from this Sasaki-Einstein 7 manifold, all the Sasaki-Einstein 7 manifolds are nearly parallel these manifolds. So, and Sasaki-Einstein 7 examples of Sasaki-Einstein manifolds are, many examples are known, so we have many examples of nearly parallel Z2 manifolds. And moreover, next we consider 3 Sasakian 7 manifold. Here 3 Sasakian manifold is a Riemannian manifold whose cone is a hyperkähler manifold. Well, hyperkähler manifold is a Calabi-Yau manifold. So 3 Sasakian manifold is Sasaki-Einstein, so it is nearly parallel Z2 manifold in this sense. But moreover, 3 Sasakian 7 manifold admits the second metric Z prime and whose holonomy group of Z prime bar is equal to spin 7. So we have many examples of nearly parallel Z2 manifolds. So and next we explain the motivation of today's talk. And we want to consider submanifold theory. So for simplicity, we assume that the ambient space is S7, 7-dimensional sphere hereafter. Well, and 7 sphere admits nearly parallel Z structure and Sasaki-Einstein structure. And in addition to these structures, there's a geometric structure coming from S6, nearly Kähler S6. So for each there's 3 geometries on S7. So for each geometry there exists corresponding submanifolds. So on S7 there exists 3 types of submanifolds. Well, the corresponding submanifolds to nearly parallel Z structure is called associative, and submanifolds corresponding to Sasaki-Einstein structure is called special Legendrian, and submanifolds corresponding to nearly Kähler sphere is called Lagrangian submanifold. Well, we will explain later that.
So you mean the Lagrangian submanifold?
Yes, 6.
S6.
Yes.
I6.
Right. Yes. So, and I will explain later that these submanifolds are following these relations. Special Legendrian and 0 times Lagrangian. So, well, I will explain later that there exist these relations, namely special Legendrian submanifolds in fact associative submanifold, and Lagrangian is submanifold of S6 sphere. So, and if we consider 0 times Lagrangian, then it is submanifold. Then it is associative. It is known that it is known to be associative submanifold, and associative submanifolds are known to be minimal manifold, minimal submanifold. So there are three types of inclusions. And by the way, but here, but here this is special Lagrangian, but the deformations of special Lagrangian submanifolds are considered by Professor Onita, and the deformation of Lagrangian are considered by Professor Lotte. So it is natural to consider deformation of associative submanifolds, and moreover, it is not, and we can make the next natural question, namely, how the deformation space will change if we deform the submanifold in wider classes. So I mean that we deform a special Lagrangian, not only special Lagrangian but also associative or minimal, deform in a wider class. In the same way, deform Lagrangian as associative or minimal. So we want to consider this problem, consider this question. So today I will study the deformations of these spaces, these submanifolds, Lagrangian deformation, special Lagrangian deformation, and so on, and then compare these deformation spaces. I want to study the difference of Lagrangian deformation and associative deformation, and the difference of special Lagrangian deformation and associative deformation, and so on. So, yes. Let's see. So I made a mistake. Sorry. Thank you very much. Yes. Next we define submanifolds from nearly parallel this geometry and Sasaki-Einstein geometry. Next we define various class of submanifolds in S7. So first, we define associative submanifolds and special Lagrangian submanifolds. So to define, so first define phi 0. This is a full form on R8 by 1/2 omega 0 squared plus real part of capital omega 0. Here small omega 0 is a scalar form on C4, and capital omega 0 is a holomorphic volume form on C4. Yes, and this full form is called spin-7 structure on C4. C4 is R8, so we define this differential full form. And this full form has the next property. Namely, GL8R acts on the space of full form canonically, and the stabilizer at phi 0 is equal to spin 7, the Lie group spin 7. And moreover, this inequality is satisfied. So, for each oriented for submanifold N, this inequality holds. This inequality means that phi 0 is a full form and N is a four-dimensional submanifold. So phi 0 is a multiple of the volume form. So that inequality means that alpha is less than or equal to 1. And these properties are known. And by using this full form phi 0, we can define the submanifolds. So let L3 in S7 be an oriented 3 submanifold. Then L is called associative if and only if this equality holds for N is a cone of L, where L is 3-dimensional, so the cone of the CL is 4-dimensional. So we and the associative submanifolds is a submanifolds coming from nearly parallel this geometry. And next we define special Legendre submanifolds, where special Legendre submanifolds is defined as real part of omega 0 restricted to TCL is equal to volume CL. And it is known that this is equivalent to omega 0 restricted to TCL equals 0 and imaginary part omega 0 restricted to TCL equal to 0. So from these definitions, we easily see that special Legendrian submanifolds are associative. Well, phi 0 is of this form, and if we restrict it to TCL, where L is special Legendrian, then the first term vanishes because of this property, and the second term is equal to volume CL. So phi 0 restricted to TCL is equal to volume CL, hence L is associative. So namely, special Legendrian submanifolds is associative submanifolds. Yes. Next, we give some properties and examples of submanifolds. First, here we have written here, but we remark again. So, namely, associative and special Legendrian submanifolds are minimal submanifolds in S7. Well, and we give some examples of special Legendrian and associative submanifolds. First example is very basic example. Namely, here R4 is a real part of C4 and considers the intersection of S7 and R4. Then it is known to be special Legendrian. This can be proved very easy, so we will give the proof here. Well, let Z1, Z4 to be the coordinate on C4, and write Z1 x1 plus I y1 and x4 plus I y4. And then R4 is a plane spanned by x1 and to x4 direction. Then we easily see that omega 0 scalar form is of this form, and capital omega 0 is of this form, dz1 to dz4. Then we easily see that omega 0 to R4 equal to 0, and dx1 dx4 with the volume form on R4. So we see that あ、そう、違う。あ、そう、まあいいや。まあいい。うん。そうか、こう。そうです。So we easily see that omega 0 and imaginary omega 0 restricted to R4 vanishes. So we see that So S7, in the intersection with S7 and R4 is special Lagrangian. And for more complicated example, where let L3 in S7 be the oriented 3 submanifold, and suppose that its cone CL in C4 is complex submanifold, then it is known that L is associative submanifold. So we give two examples, but in general, constructing example is a very difficult problem. It is because the reason is that associative submanifolds are defined by the nonlinear partial differential equation. But in general, it is very difficult to solve partial differential equations, so it is very difficult to construct examples. Construct examples of associative submanifolds. There are many ways of construction. For example, by using the symmetry of Lie group, cohomogeneity one example is constructed by Professor Lotte. Next, we give the definition of submanifolds from nearly Kähler geometry of S6. And we define Lagrangian submanifolds.
So, elementary questions.
Yes.
You consider associate. Do you mean associative submanifold?
Yes, correct.
And S7.
Yes.
And relative to and nearly parallel.
Yes.
To this structure.
Yes.
If you take cone, then you have a cone became spin 7 holonomic.
Cone
of nearly parallel Jitsumal.
Yes, contained in spin 7, but not equal. The standard metric on R8.
R8.
The metric on S7 is standard one.
R8.
Yes.
This is a flat spin.
Yes, a flat one. Yes.
How about is a cone of associate submanifold?
Yes.
Kelly submanifold.
Yeah. Yes.
In R8.
Yes.
In particular, it is minimal.
Yes.
So any associate submanifold in S7
yes.
is always minimal.
Yes. Yes. Well, it is known that the cone is minimal submanifold if and only. Yes. Yes. Next, well, we will next define the Lagrangian submanifolds. Well, as in the former case, there is a 3 form on R7 such that the stabilizer at phi 0 is equal to the exceptional Lie group Z2, and for each oriented for submanifold N, this inequality holds. Here star is a Hodge star operator, so star phi 0 is a 4 form on R7. So this is the same property of capital phi 0. And by using this phi 0, we can define Lagrangian submanifolds. Namely, let M3 in S6 be an oriented 3 submanifold. Then M is called Lagrangian if and only if this equality falls when N equal to the cone of M, Cm. And this condition is known to be equivalent to this condition. Phi 0 restricted to TCM is equal to 0. But next we will explain why this submanifold is called Lagrangian. First note that this phi 0 is of the form phi 0 equal R dr wedge rho plus R cubed psi plus. Here rho is a 2 form on S6 and psi plus is a 3 form on S6. We can define phi 0 of this form. So if we consider phi 0 restricted to TCM equals 0, this is equivalent to this form vanishes. Well, here I is an inner product, and R del del R is a position vector in R7. So by considering this form, this condition is equivalent to rho 2Tm equal to 0. So rho is a two form, so the restriction of two form vanishes, so M is called Lagrangian. Yeah. Yes. And next we use a similar remark as similar remark. So first, Lagrangian submanifolds are known to be minimal submanifolds. This fact is known by Professor Ejiri. Yes, it's minimal submanifold. And next we remark that. Next we use a relation between capital phi 0 and small phi 0. Well, under the identification R8 equal R plus R7, capital phi 0 can be described in this way. So here x0 is a coordinate on R. Yes. And from this relation, we easily see that 0 times Lagrangian is associative submanifold in S7. Well, 0 times Lagrangian has no x0 direction, so the first term always vanishes. So the rest is, and the second term restricted to the cone of Lagrangian is equal to volume form of cone. So by definition, 0 times Lagrangian submanifolds is associative submanifolds in S7. As a former section, we give examples of submanifolds in S7. It's 6. Well, denote IR be the imaginary part of C3 and consider the intersection of R times IR cubed and S6. Then it is known to be Lagrangian in S6. And in general, for oriented 3 submanifold M in S6, if its cone is of the form point times complex submanifold in C3, then M is known to be Lagrangian. So these are the examples of Lagrangian submanifolds in S6. And as associative or special Legendrian submanifolds, constructing examples is difficult because these submanifolds are defined by partial differential equation. And by using the symmetry of Lie group, cohomogeneity one example is constructed by Professor Lotte. And I also constructed the example with slightly different method. And we obtained the examples of Lagrangian submanifolds in S6. So here, now we define each submanifold, special Legendrian, associative, and Lagrangian submanifolds. So next we want to consider the deformations of these submanifolds. First, we want to explain the idea of infinitesimal deformations of submanifolds. Yes. First, the setting is this. So let Yg be in a Riemannian manifold and let L in Y be in a submanifold. And let Lt be in a family of submanifolds of Y with L0 equal to L. So here, now we want to consider the infinitesimal deformations. So we want to, roughly speaking, we want to consider the differential of a submanifold. So, and we want, but it is not not good good description. So we want to formulate this mathematically. So to formulate this mathematically, we use the normal boundary of L in Y. We write this nu. Here, and well known the tubular neighborhood theorem. The neighborhood of zero section of nu is diffeomorphic to tubular neighborhood of L. So by exponential maps. So via this diffeomorphism, the sections of normal boundary with small norms corresponding to submanifolds close to L. So it is natural to consider. It is natural to regard the differential of submanifolds as the differential of sections. Of course, ST corresponding to LT. So we may study the differential of sections, and by using this idea, we study the infinitesimal deformations of submanifolds. Next, and by using this idea, we obtain the next theorem. Yes, we summarize this. Yes. First, let A in S7 be an associative submanifold. Let L3 in S7 be special Lagrangian submanifold. Then the statement 1 is well known. So the space of infinitesimal associative deformation of A is identified with this space. Here D is some differential operator on C infinity A nu. So minus 1 eigenspace of some differential operator D. So the deformation of associative submanifolds. And next we study the infinitesimal Lagrangian deformations, special Lagrangian deformations of L. Yes, this result is obtained by Professor Onita, and this space is identified with the eigenspace of Laplacian on L. Laplacian plus F equal A to F. So this case, special Lagrangian case. And now, next we consider the deformation of special Lagrangian submanifolds as associative submanifolds. So in this case, we obtain this result. Here ROT, we call this rotation operator. This is a differential operator on the space of vector fields. And the infinitesimal associative deformation of L is equal to dimension the 8 eigenspace of Laplacian. This space is the infinitesimal special Lagrangian deformations of L. So the difference of special Lagrangian and associative deformations are given by this second term. So the difference of this and of this manifold is given by the minus 2 eigenspace of the rotation operator. And next we assume that M3 in S6 being oriented let M3 in S6 be a Lagrangian submanifold in S6. Then statement 4, it is well known that infinitesimal Lagrangian deformation of M is identified as 3 eigenspace of the rotation operator. This is the same operator, rotation. And if we deform Lagrangian submanifolds as associative submanifolds, then we obtain this next result. And the first term is the dimension of infinitesimal Lagrangian deformation of n. So the difference of Lagrangian submanifolds and associative submanifolds are given by this term. So 3 eigenspaces of the Laplacian on M. So first we obtained this theorem. And here we assume that the ambient space is S7, but we can generalize ambient space S7. So S7 to Sasaki-Einstein submanifolds or sine cones of nearly classic manifolds. Next, we give some remarks about the differential operator D or rotation operator. First, we give a remark about the operator D. Well, it is known that there exists a rank 4 vector bundle E over A, and nu is isomorphic to S times S tensor E. Here, where S is a spinor bundle over A. So then D is known to be a twisted Dirac operator. Yes, this is a twisted Dirac operator. And next we give a remark about the rotation operator, where we can identify with tangent bundle and cotangent bundle by the metric. So then the rotation operator corresponding to this operator, D is different exterior derivative and star is a Hodge star. Here L is 3-dimensional. The image is contained in omega 1 L. Yes. And now it is known that D is a twisted Dirac operator, so it is natural to expect that D squared has a good property. In fact, if D is a usual Dirac operator, not twisted operator, then D squared is equal to Laplacian. So then we consider the squares. Then we study D squared and obtain this result. And D plus identity nu times D minus 3 identity nu is equal to J. Here we mean that J is a Jacobi operator. Jacobi operator is identified in this way. So namely, J psi equals 0 if and only if psi gives infinitesimal minimal deformations of L. Deformations as minimal submanifold. And so if we set D psi equal minus psi, then we easily see that J psi equals 0. And since we know that associative submanifolds are minimal, so this relation ensures that the associative deformations are minimal deformations. And by using this formula, we can define minimal deformation of associative submanifolds. So to consider minimal deformation space, we only have to consider the 3 eigenspaces of D. So these are examples. Yes. Next we give outline of proof. First we give an outline of proof of statement 1 and 2 and 4. Here at 1 and 2 and 4 is a standard deformation. Namely, deform associative submanifold as associative submanifolds, and deform special Legendre as special Legendre submanifolds, and deform Lagrangian as Lagrangian submanifolds. Standard deformation. So to prove this statement 1, 2, and 4, we assume this fact. Namely, associative submanifolds, special Legendrian submanifolds, and Lagrangian submanifolds are defined by vanishing of some tensor alpha. Which I mean this. So if we set the if we set this function f, this is a function c infinity m nu to the space of the sections of tensors by v to exponential v star alpha to tm. We consider this function. Then we easily see that exponential Vm is associative if and only associative, special Legendre or Lagrangian if and only if Fv equal to 0. So to study the infinitesimal deformation of associative, special Legendrian or Lagrangian, we may consider this, the differential of f. So 0 equals df0 to v, and f can be defined by the exponential map. So this is equal to lead derivative by v. So and considering this, by calculating this, we obtain statement 1 and 2 and 4. Yes, 1, 2, and 4. We can obtain in this way. We may only consider the lead derivative of the tensor alpha. So we can prove statement 1 and 2 and 4. Yes, and next we give an outline of proof of 3 and 5. Yeah, these 3 and 5 are my results. And the 3 is deformed special Legendrian as associative, and statement 5 is deformed Lagrangian as associative submanifold. Yes. So we only prove 3. The proof proves 3. The proof of 5 is the same as that of statement 3. So to prove this, first we use the fact that if L is special Legendrian, then the normal boundary is identified with TL tangent boundary plus R. So first we consider the rewriting the operator D. And so via this identification, D is operator from chi L to C infinity L to chi L to C infinity L. And the corresponding operator can be described in this way. So corresponding operator can be described by gradient, rotation, and divergence. These are operators which can be seen in vector analysis. And then next we try to prove the formulas of vector analysis. These operators have the same property as in the vector analysis. So for example, for any smooth function f, and for any smooth vector field v, rotation gradient f equals 0 and divergence rotation v equal to 0. So by using this, we can prove over 3. So to consider the associative deformation of special Legendrian, we only have to consider the -1 eigenspace of D. So first we set dVf equal -Vf. Then from this proposition, we obtain that we easily see that this equation is equivalent to this. Rotation v plus 2v equals gradient f, and divergence v equals -4f. And these two equations are equivalent to these two equations, which can be seen very easily by using the lemma. So So to prove the equivalence of these two equations, we consider the divergence of the first equation. Then take the divergence of the first equation. Then we obtain this. The yes, from that lemma we easily see this relation. So comparing this equation and this equation, and we easily see that this is equivalent to this. And from this equation we see that for each smooth function f satisfying Laplacian plus f equal a to f, Vf equal 1/2 gradient f is a solution of these two equations, which can be seen from this lemma. And it is known that this corresponding to the infinitesimal special Lagrangian deformations of L. So for each f with Laplacian plus f equal a to f, there is at least one solution of this. And to obtain other solutions, we only have to set f equals 0. Then we obtain rotation v plus 2v equals 0, and which implies the proof. This is rotation v plus 2v equal to 0. So we obtain this theorem. So, and finally, by using these formulas, we explicitly study the deformation space of homogeneous associative submanifolds in S7. Well, but homogeneous associative submanifolds in S7 are classified by Professor Lotte, and he has the following result. He obtained the following result. Let A in S7 be a connected associative threefold with the orbit of a closed three-dimensional real subgroup of spin 7. Then, if A is contained in totally geodesic S6, then A is known to be Lagrangian. Or if A is not contained in S6, then up to the spin 7 action, A is either A1, A2, or A3. A1 is diffeomorphic to T3, 3 torus, and A2 is diffeomorphic to SU2 over Z3, and A3 is diffeomorphic to SU2. And the first case, the homogeneous Lagrangian submanifolds are classified by Professor Massimo. And the deformations of Lagrangian submanifolds are considered by Professor Lotte. This part is already known. So we mainly focus on the second part, A1, A2, and A3. So and next we give some property of A1, A2, and A3. First, A1 is a special Lagrangian submanifold given by Harvey and Lawson. This is perhaps it is the first known non-trivial examples of special Lagrangian submanifolds. And then about A2, and if we consider the cone of A2, then it is a complex submanifold in C4. And A2 can be described as SU2 over Z3, but A2 is in fact U2 invariant. And A2 has more interesting properties. So, and by spin 7 action, A2 can be deformed to A2 prime, and A2 prime in C4 is special Lagrangian, which is obtained by the irreducible representation of SU2. Very, very interesting examples. And the case of A3, the A3 is associative submanifold not arising from other geometries. So A3 is not special Lagrangian or Lagrangian. So a genuine associative one. So for each A1 and A2 and A3, we study these deformation space. We study deformation space of A1, A2, and A3. Then we obtain the next result. Here, we give dimensions of infinitesimal deformation spaces of A1, A2, A3 in the next list. First, this list means that if we deform A1 as associative submanifold, we obtain 18-dimensional deformation spaces, and A2 has 13-dimensional deformation spaces, and A3 has 34-dimensional associative 34-dimensional deformation spaces. The next column is about means that if we deform A1 as minimal and non-associative submanifold, so we study the difference of associative and minimal, and the difference is given by the dimension of the difference is given by 7. And in the case of A2, the difference is given by 6. In the case of A3, the difference of this over here given by 12. But we note that the spin 7 is the automorphism group of the S7 with nearly parallel this structure, so there is a trivial deformation of associative submanifolds. So first we count the dimension from this automorphism group spin 7. First, A1 is T3 invariant, and spin 7 is 21-dimensional, so the trivial deformation induced by the spin 7 action has 18-dimensional. And A2 is U2 invariant, so U2 is 4-dimensional, so we have 17-dimensional trivial deformations. And A3 is diffeomorphic to SU2, so we have 18-dimensional trivial deformations. And next we study O8 minus spin 7 action, and we obtain the 7-dimensional. 7-dimensional is we have trivial 7-dimensional deformation of A1. And in the case of A2, we have 6-dimensional trivial deformations, and in the case of A3, we have 7-dimensional trivial deformations. So if we compare these two results, then we see that AY is listed as associative submanifold. This is 8. The deformation space is 18-dimensional, and trivial deformation have 18-dimensional dimension. So AY is listed as associative submanifold, but in case of A2 and A3, A2 and A3 are not listed. 30 is larger than 17, and 34 is larger than 18. But in case of A2, we can explain this 30, all of 30-dimensional deformations, and the associative deformation of A2 can be explained by spin 7 action and deformation as a complex cone. Well, we will remark that first we remark that if the cone is complex submanifold, then L is associative. So if we deform submanifold, if we deform CL as complex submanifold, we have a complex deformation. So by spin 7 action and deformation as complex cone, we associative deformation of A2 are obtained. And next result is about the second column. Anyway, minimal and non-associative deformation of A1 and A2 is trivial. Here 7 equal to 7 and 6 equal to 6. But A3 can have minimal but non-associative deformations. 12 is larger than 7, so we obtain this result. And we obtain this result, and we use the technique of Peter-Wild theorem. This Peter-Wild theorem is a generalization of Fourier series expansion on torus. By approximating the very good function, we try to solve the differential equation. We calculate the dimension of the eigenspace. We calculate the dimension of the eigenspace. So, and by using this theorem, we obtain the next result. So, A2 plus has a non-trivial associative and non-special Legendrian deformations. So A2 prime, sorry, A2 prime is this, so this special Legendrian from A2. So this is very complicated. So we give some summary on this black whiteboard.
So you say S3 can have no trivial deformation.
Yes, but I do not find it is actual deformation. So I don't know the integrability. I don't find it. I don't find that. But, yeah. So from the theorem. From that theorem, we have for convenience we use this clause, which means some submanifolds can have deformations, and circle means all deformations. Manifolds are trivial. So from the first lemma, we see that the difference of associative, where A3 can have non-trivial deformations. So from this. By using this notation, we see that associative, the difference of minimal and associative is we like cross.
Homogeneous case?
Yes, yeah, homogeneous case. Yeah. Yes, hi. Homogeneous. And from the next theorem, we see that this is equal to the cross. But if we consider Lagrangian, if L is a homogeneous Lagrangian submanifold in S6, then associative and non-Lagrangian deformations of L is trivial, which comes from spin 7 minus Z2 action. So here, this inclusion is we make circle. But some of L can have non-trivial minimal and non-associative deformations. So this inclusion we write cross. So that we should study here special Legendre deform. We should study here, but to study this part, we need the classification of homogeneous special Legendrian submanifolds. But I do not know such a result, so I don't know if this is cross or circle. But from these theorems, we obtain this result. So finally, we give some questions. So well, there's only one circle. So why are associative and non-Lagrangian deformations are trivial? Why this is only this is? What is the geometric reason of the difference? Why this is only circle? And if we find some reason, so if we find some reason of this, then next we want to consider, can we drop the assumption of homogeneous? Namely, for any Lagrangian L in SX are associative and non-Lagrangian here, deformations of L is trivial. So these questions we want to consider next. So I will finish my talk. Thank you very much.